computer. Okay, we're going to continue with thermal properties. The first one we did was talking about most of the stuff that was in the book. I'm going to finish out what's in the book, but I'm going to add kind of a review article that summarizes all the things we talked about that were in the Koo book. Okay, so we're going to continue on with that. And let me start here. So we kind of stopped, I think, about here where we were talking about the thermal conductivity of a material as you add different materials, as you add stuff into it. And there was, in many cases, a place where a certain loading will do really well, and then above that loading, it doesn't do very well at all, okay? And so most of the time when that happens, we think what's happening is that in some of the loadings, we see very finely dispersed materials, but at some point, there is this self-aggregation energy that allows it to form larger aggregates. And in this case, this is what happened in the higher loadings of the multi-walled carbon nanotubes. They started aggregating, and when they aggregate, they're not distributed into the matrix, therefore they do not contribute to the thermal conductivity of the bulk. Okay, so that being, I'm sorry, I started early. I apologize.
Sorry, I'm always late because I have a class right before it, so I'm just jumping between.
Okay, so that means that maybe there is some other way to modify these carbon nanotubes to make them better associated with our matrix. So in this particular study, what they did was they took pristine multi-walled carbon nanotubes. Then they took another batch and took them and acid treated them with phosphoric acid. So what they're trying to do is get the surface to be, modified on that. But then they also took this benzene tricarboxylic acid and surface modified it so that it would, have these carboxylic acid groups actually functionalize. The benzene ring is probably stuck to the surface there, and the carboxylic acids are in the matrix. And so what they found was as they increased the loading here from 1 to 3 to 5%, we saw that the pristine ones are the lowest right here, giving their lowest thermal conductivity. The second one was the acid right here. Now this is the model here that they use. It's a volume fraction of conducting material. What conductivity should a volume fraction of a conducting material give, given that particular state? And so this is the theoretical line here. But what they found was when they treated it with this benzene tricarboxylic acid here, they got the much higher thermal conductivity branch, and then they were above that of the predicted model based on volume fraction. So that means there's something aiding in its mixing with the matrix and its interface with the matrix. I'm going to talk about the interface with the matrix in the second half of this. Okay. So that was a really good thing that they figured out, and it was a pretty significant difference there. And what they found is at even a low loading, right here, even this 1% loading, they got a 315% increase in thermal conductivity. And they had very well dispersed materials right here. So this is the pristine one right here. And so there's a lot of aggregating here. And this is the treated one. We don't see any of them sticking out of the matrix. It's almost like they're buried in the matrix and well incorporated into the matrix because of the surface modification. Okay, because we can see these pulling out of the matrix and bundles in the matrix when they're not modified. So the surface treatment makes it really good for getting it into that matrix. And so there is another model that says you have the thermal coefficient of the polymer itself. So it's going to go through the polymer at whatever rate the polymer is going to go through. And then there's an interface between the polymer and the nanomaterial. There's an interface there, and there's a bit of resistance. If you can lower that resistance in that, then once you get to the nanomaterial, that's usually the highly conductive, and it shoots. The photon shoots to the end of it, and then it has a barrier where it transfers from the nanomaterial to the matrix, goes through the matrix. And so you can think of it as a series of resistive steps right there. The longer a persistence length you get with your nanomaterial, and the fewer of those interfaces, the better. Or you improve the thermal conductivity of the interface, If you improve the thermal conductivity of the interface, you actually have a less resistance to go from matrix to filler, matrix to filler, matrix to filler. Okay. So that's what I think they're doing here is they've got a much better interface between the matrix and the filler. They've decreased that resistance, thermal resistance. Okay, what are you doing?
The BTC?
BTC is benzene tricarboxylic acid treated multi-walled carbon nanotubes. Okay. So when they looked at it, they looked at the two different ones in pristine state. They saw a lot of bunching up in there, meaning that they would rather aggregate with themselves than interface with the matrix. Okay. Now with this, with the the phosphoric acid treated one, they saw a little bit of dispersion, but they also saw some aggregation. There was a little bit better dispersion, so that's why the conductivity was slightly higher. But they still had aggregation here. And if you look at this blow up of the aggregation of the phosphoric acid treated system, you'll see that they're kind of bunched up together. But when this is the carbon, the benzene tricarboxylic acid treated one, and notice that there are very few bundles, or the aggregates are very small, or they're very small bundles of them, and they're distributed more evenly through the system. So that gives us a reason why we get to that higher thermal conductivity, because these have a better that are more easily dispersed into the matrix, and might even have that lower thermal barrier to go from matrix to filler. Okay, we can see the same trend in expanded graphite plates. And so they did small graphite plates, medium graphite plates, and large graphite plates. Okay, why do the large graphite plates have a better, higher impact on the thermal conductivity?
Because there is more restrictive movement.
Okay, because remember, there's when you're in the filler, you're going very slow with your thermal conductivity. When you're in the conductive material, you're going very fast. The longer that persistence length of that continuous high thermal conductivity area, the better. Now, also, what's the benefit of the graphite carbon plates versus the single-walled carbon nanotubes? Single-walled carbon nanotubes basically transfer thermal conductivity in one direction. They have thermal conductivity in one direction. They are a two-dimensional nanomaterial, but they have thermal conductivity in one direction. The plates have thermal conductivity in two directions, even though they're only one dimension. So you might have your threshold happen a lot sooner with your graphene plates, especially if you're going to align them. Okay. So we see that kind of nice trend here. The smaller plates have the lower persistence length. The medium plates have about better, but we have a nice sharp turn on here. And this probably, if they did a few more points, they would have gotten a nicer curve. So we're looking at different ways to get different kinds of conductivity, thermal conductivity here. And choosing your filler and choosing your polymer, depending on whether you want a biaxial transfer or just a uniaxial transfer, you can pick your material and or your alignment technique.
Does
Yes.
it change the specific surface area?
Okay, it probably changes it some. But I mean, when we're talking a fully exfoliated graphite per unit mass, it probably has the same surface area per unit mass, because we're just adding more edges, and the edges are the small side.
It's about the direction, the change,
Oh.
variation.
Oh, you mean the
Yeah,
cross-sectional area?
like for multiple single-walled carbon nanotubes.
Well, it does have a little bit to do with surface area, because that's your thermal interface with your matrix. Okay, but it's also, how many, like, you would have to have two multi-walled carbon nanotubes crossing at some point, touching, to be able to transfer heat in two different directions. Does that answer your question?
Yeah.
Okay.
So there has to be a low surface area to have that continuous.
No, you actually want a high surface area because you want your matrix to have as much full contact with your device as possible, your thing as possible.
So if a nano material is of longer for a smaller surface area, it would be have longer than transparent, because there would be a breakage if it has a high surface area.
I think it's more a function of aspect ratio than surface area. Because what you want to do is transfer as far as possible in your highly conductive material before you have to jump into the matrix and then jump on for. So, and what you might see is that, even if you have tubes crossed in the middle, your phonon still might go to the end of your length and then try to transfer to the matrix. It's not going to back up and try to go off a different path, but it might head off in one direction if there's a thermal gradient or something to make the thermal phonon to go in that direction. Does that make sense? Okay. Let's see. So when they tried to do this, they wanted to even enhance that, two-dimensional spread, get those large plates as dispersed as possible. So one thing they did here was they modified the surface of the graphene with this silane material here. And what it's going to do is that silane here is going to clamp onto any hydroxyl on the side edges of the plates or in the middle of the plates, leaving that amine to be able to bind into the matrix. Remember, the amine is going to react with an epoxy. Now you have a covalent bond between your graphene and your epoxy. So I said before, tighter bonds, smaller atoms, less thermal interface gives you a higher thermal conductivity in the bulk because it reduces that resistance to jump into the matrix and jump back onto the thing. So what they saw when they functionalized it with this amine that's physically, chemically binding to the epoxy is they saw an immediate jump in there and a much better increase in the thermal conductivity.
It's not covalently binding to filler though, right?
If there are defects in the graphite, and there are usually defects along the edges that have hydroxyls, they can be chemical binding. If there's defects, like a graphene oxide would have a lot of hydroxyls on the surface, it would chemically bind to that.
So it would displace one of those.
It would, this silicon would displace one of the OHs, and then it would spit out an alcohol, and you would have a covalent silicon oxygen carbon bond. So, and this works a lot with the graphene oxide because then you only partially reduce it because the silane can stay there. So what they saw when they kind of used these in an epoxy is that when they did their freeze fracture on there, the epoxy, the platelets just kind of fell out. They just kind of pulled out of the system and they weren't well adhered to the matrix. But when they did it with the chemically treated ones, they saw that when they pulled them apart, it was very well bound to the matrix, and they had a very different architecture. There were free-flowing ends of graphene platelets that actually broke along where the matrix broke. So it's showing that's very well chemically adhered, very well adhered with the matrix, and therefore should lower the thermal barrier from matrix to filler. And they saw the same thing with the expanded graphene nanoplates. In expanded graphene nanoplates, obviously, you put something in between them, and then you heat them really high, and it kind of makes this graphene-like foam. And then when you intercalate it here, notice these are really low loadings. This is the polymer by itself, and this is a 2% here. And we get almost a 50% increase in the thermal conductivity with that low material. It's significant, but I mean, it's not like you're going to use it in a motor or anything as a heat sink. Okay, so the last thing I think we had in the book was this graphene oxide multi-wall carbon nanotube. So in this one here, they're taking advantage of the long needles and the platelets, okay? And in addition to that, they're taking an approach where they're getting pre-arrangement, okay? So they're dispersing them in liquids. They're letting them settle out into a material, and then it's cooked down until it makes not cooked down, it's sucked down to make it kind of, so all the platelets are like laying down on each other, and then multi-walled carbon nanotubes are woven in between it. Okay, so they're pre-ordering it to have a plane where a lot of the plates are aligned and a lot of the tubes are aligned. They're going to be lined in the XY plane here. And so this is the Z plane right here. And then when they took it, they knew they had a porous material, and when it was annealed, and then they infused it with epoxy, then they cured it. Okay, so when they do this, what they see is that there is a synergistic effect between having the carbon nanotubes and the graphene oxide platelets in there. So if we just had the graphene oxide by itself in the epoxy, we get this thermal conductivity. They don't have just for the carbon nanotubes. But then when they have with the, let's see, where's this is, where's the, oh, yeah. We're adding carbon nanotubes here, and we get a percent enhancement of 140% just at this loading here, okay? But notice that we have a drop off as the loading gets too high, okay? Okay, what can account for the drop off when the loading gets too high?
They're not fully dispersed.
The loading is so high, we're actually not getting enough of the matrix in there, and we have air. Okay, because there's no epoxy to help transfer the phonons. It's trying to transfer through air. So that's one of the explanations, because right here, this is a very high loading. How are you going to get all the holes and pockets in between there just by infusing it with an epoxy? That's kind of hard to do. So I think that they might have that happening in this. So again, a moderate ratio of graphene oxide to multi-walled carbon nanotubes is important. Now again, graphene oxide is not as conductive, thermally conductive as graphene. So, but they did center it. So there should have been a conversion of the graphene oxide partially to the graphene. They centered it at 1,000 degrees. No, only 100 degrees. So that's, if they had centered it at 1,000 degrees, they might have got a higher thermal conductivity there. Okay, so, and of course, this all kind of goes down. We've talked about this a little bit, but I wanted to show this diagram because it's kind of cool. Looking at the heat flow. If you have well-dispersed carbon nanotubes, you're going to have more than one thermal pathway. Okay, if you have poorly dispersed carbon nanotubes, in this case, we're only going to have, this set is going to be the thermally conductive set. These are thermally isolated from each other. So it has to transfer through this very quickly, then transfer through the matrix to the next one, then transfer through the matrix to the next one. It doesn't have that continuous path because it's not well dispersed. It has the aggregates. In contrast, when we have this here, that's a thermal pathway, that's a thermal pathway, that's a thermal pathway, that's a thermal pathway. When they're more dispersed, you have more thermal pathways. More thermal pathways equals higher thermal conductivity. Okay. Questions on that? Okay. So this is what was in the book, by the way. So yes.
They have just used the epoxy as a base material. Do you think they will affect the properties by using polyester?
The polyester actually has a lower inherent thermal conductivity. So I think, well, it depends also, because in the epoxy, you're looking at different ways of doing, you only have a set it and forget it kind of thing. In the polyester, you can reprocess it, disperse it again, stretch orient it. You can do a bunch of different things after the fact. The epoxies, because they're the thermosets, however it was when it cured, that's what you get. So yes, you probably can get enhanced properties, not just by the polyester itself, but by the fact that you can process it afterwards. Okay, so this next section here, I wanted to do because I think it ties together everything we talked about in this chapter. but it's not as well outlined as in this paper. So the paper here is listed below on the slides here. And so they go over two different aspects for making thermally conductive polymer and polymer nanocomposites. So the idea here is that there are some physical mechanisms that you can do on just the polymer. I told you that if you have tight bonds, small atoms, and really good, really crystalline materials, you're going to transfer heat faster, okay? And we're going to see that in this set here. But then when you have your nanocomposites, you want to talk about without an interfiller network and with an interfiller network. And so by having your networks kind of being well dispersed versus uniquely processed, we can get to different things. And then by looking at different fillers and how they affect things, there we go, different fillers, single fillers, hybrid fillers, and then three-dimensional foams. And I think there's some really cool stuff here in the hybrid filler section that we'll talk about. Okay. So just now for the polymers, how are we going to enhance thermal conductivity in polymers? Okay, just the polymer by itself. So we said that we're going to be transferring heat from atom to atom to atom as we go. And so one of the best ways to do that is to get all of our polymer chains aligned by stretch ordering so that number one, you have a long persistence length along the axis of the stretch, and you have enough, you have a lot more interface between the inner chains that can, when the phonon hops from one chain to the next, it can continue on in that direction. So what we see here in this case here is if we have a microfiber or a film of this polymer, and this polymer is called UHMWPE, which means ultra high molecular weight polyethylene. Okay, ultra high, regular high density polyethylene has about every few chains has a little branch with 4 carbons on it. It's because of the mechanism of the reaction. But in ultra high density, ultra high molecular weight polyethylene, you actually have very few side defects. So now that classical picture of the zigzag that you drew, now you have all of them stacking together perfectly in zigzag. So your crystallinity can come up. Okay. In fact, if you draw out fibers, it's called spectra fiber, and it competes with Kevlar for bulletproof vests. Okay, it's that tough. Okay. So in this case here, when they had the microfibers of it, they saw that the thermal conductivity goes up withdrawal rate until a little bit. Okay, and so when you think about that, you might think that there's microcrystalline domains that aren't aligned with the fiber. And again, they're looking at thermal conductivity along the axis of the fiber. But in the nanofiber, you don't have enough room for these microcrystalline domains. And so you get more and more aligned crystalline domains, not phases separated out from the line. And so you end up with a higher thermal conductivity. Now, when you get this here, notice the crystallinity actually decreases as you do this stretch. Okay, so instead of having these little crystallites that spread out into the matrix, you actually are destroying some of the crystallites to get everything aligned more perfectly. Okay, so it's not the crystallites themselves, it's the actual chain alignment here. So that's a second order effect. It's not that primary effect. And they showed that they could do the same thing with these two things. And it wasn't a polymer, so I didn't think about it. So the next thing we can do is we can nano template. Okay, so that's going to template it so that as you're growing the polymer, it grows in an orderly fashion. So in this one, this is actually kind of cool. What they're going to do is they're going to electrochemically grow a polymer. Okay, but they're electrochemically growing a polymer with a nanoporous template. So the actual electrode, the working electrode that they're going to grow the polymer from, has this porous material put on top of it. So it has to grow through the little channels in the pores. It has to grow up through the little thing. As it's doing that, there's only a space for maybe a few chains. Okay, so if you grew this on the surface of a bare electrode, you would have them growing all over the place like this and kind of going in all different directions. Just wherever they found the next monomer is the direction they grow. And that would look something like this. But when you restrict them in that tube, they have to grow from the end, and they have to grow where they have the volume to grow. So they're all aligned in the system. And when they do that, you can get this pre-ordering here. And that pre-ordering also gives you higher thermal conductivity. Remember, one of the fillers we used last time was polythiophene. Polythiophene is a rigid polymer and has a higher thermal conductivity than the epoxy itself. And here is a good way to get it aligned. And then you infuse epoxy into it. Now you have all of your, after you take your template off, you can infuse it in epoxy, and you're going to have higher thermal conductivity in the z-axis than in the x and y-axis. So you'll actually have directional thermal conductivity. Okay, see how that templating would work to give us directional thermal conductivity? Okay. So then another thing we can do is called electrospinning. Anybody know what electrospinning is? We have an electrospinner here on campus, by the way. So electrospinning is where you take a polymer solution and you charge it up to about 5,000 volts, and then you slowly pump it out of a very tiny needle, and then you have a ground plate somewhere away from it. And what happens is the polymer solution is accelerated to the ground plate by the potential, the electrical potential. And as it does this, it draws the fiber out. In fact, most of the time, most of your fibers you get out of this are submicron in the nanometer range. And you can get fibers down to 50 nanometers, 10 nanometers using this method. It's a very easy method to get polymers down to that method, other than the safety interlocks and stuff. But most of the time it's done in solution, but you can do it in melt. Okay, so imagine you're shooting this solution of polymer, and as you're shooting the solution of polymer toward the ground plate, it's starting to evaporate. The solvent is evaporating, okay? And so it's being drawn out by the electrical current, and the solvent's evaporating from around the sides. So the chains are aligning and then compressing into bundles, okay? So they're gonna be aligned along wherever that fiber was shooting. So if it's a very fast, very small fiber, you have what we call the just aligned chains, okay? And so all the chains on the outside surface and on the inside surface are all aligned in the same way and at the same density. This is preferential because now we have a great transfer of heat between, on the XY axis as long as the Z axis, which is our long axis in this one. But if you only align if it evaporates too quickly, it'll form a shell. And so only the outside is going to be aligned. And then the inside is going to have a core that had more or less liquid in it, and it's going to be less ordered. And so only the outside is going to give you a thermal conductivity. The inside is going to be more disordered. And then if you spray it really too slow, or you have a very crystalline polymer, what's going to happen is it'll start crystallizing as soon as it comes out of the needle, and you'll end up with these little crystalline phases. Oops, let's change color here. You'll end up with these little crystalline phases followed by the bulk polymer matrix. Okay. So in our case, the best case scenario is it's shooting out and evaporating, and as it's evaporating, it's ordering and forming fiber bundles in that Z direction. Okay, so that's how the electrospinning does. And actually, another way that they do order in electrospinning is if you do it on a drum, it'll order all of your fibers in a direction. So all your Z's are going to be in the same direction. And you can even do it where you raster it, where you have first you put a whole bunch of fibers in this direction, then you put a whole bunch of fibers in this direction, and you can do them back and forth, so you can actually get thermal conductivity enhancement in that XY plane. So that's another way to do order in the system. All right. So I said before that small tight bonds, small atoms lead to thermal conductivity. So this is showing you the chain rigidity. The tighter, the less flexibility the chain has, the higher the thermal conductivity is. So in this case here, we have a comparison between polyethylene, so right there, and polyacetylene, which actually isn't, it's made from acetylene, it's not acetylene. Okay, so here we've taken out free rotation in one of those bonds. Okay, and what we see is the thermal conductivity of, as we get longer and longer polymers, actually continues to go up in the polyacetylene here. And it has everything to do with this being a tighter, stronger bond than this, and therefore it has enhanced thermal conductivity. So this is just the polymer. We haven't even added a filler yet. So we have that kind of enhancement in there. Now, we can see that in more common polymers too. So this is polyethylene again, right here. But what we've done is we've changed it to, this is benzimidazole. Benzimidazole is a industrial polymer, high temperature polymer. It is very rigid across the system. It only has this one bond that can rotate, but it also has, excuse me, hydrogens there that can hydrogen bond. I'm going to talk about hydrogen bond next. Nitrogens with hydrogens on them, yeah. There's a nitrogen without a hydrogen, a nitrogen with a hydrogen, so it can hydrogen bond in between chains, okay? And then there's polyparaphenylene, which is a rigid polymer, but it is not hydrogen bonding, okay? So let's look at the curves here. So if we look at the benzimidazole here, we have this nice linear correlation with, as you increase the length of the polymer chain, the thermal conductivity increases. So it gets, the phonon gets to travel as far down the chain as possible and then jump. The next one is the benzene. It's more rigid than polyethylene, so it does increase with chain length, but it's not as good as the benzimidazole because of the hydrogen bonding, making the chains tighter to each other, okay? It has the same rigidity because it still has only that one place of rotation. And then there's actually going to turn out to be that the dihedral angle between them also affects things too. Okay, so let's look at some other ones here and look at for the flexibility or the changing in atoms. Okay, so this is polyethylene oxide. This is polymethoxide. What do they call this? Polymethylene oxide. It's also called Delrin. Polyethylene, and then the phenylene here. So the addition of the oxygen here, the addition of a slightly heavier atom with more flexibility is decreasing the thermal conductivity. So only carbon atoms, rigid carbon atoms, adding this oxygen. Now remember that oxygen, it's going to give a kink in your bend, and there's not hydrogens here. There are lone pairs. So it's going to give you a different interaction with the system and actually has lower thermal conductivity. And then this looks like it's polyphenylene oxide. So even if you take this polymer, this rigid system, and put that oxygen kink in it, it lowers its thermal conductivity as well. So even the chemistry, even the chemistry of the polymers is important to our thermal conductivity studies. Okay. And like I said before, dihedral angle, okay? So when we look at dihedral angle, we're thinking about if you have a rigid thing, how are they aligned at 90 degrees? Are they aligned at 15 degrees? Most benzenes are between 15 and 30 degrees if there's nothing substituting them, okay? So the lower the dihedral angle, the higher the thermal conductivity because the better it can stack with the other polymers here. So let's look at, let's see, which one best shows that? Thermal conductivity in the XYZ direction. I thought one of these showed a really good expression. Oh, and then, so what they were able to do after measuring the thermal conductivity of these isotropic or single direction ones with having three different axes here. So it starts, but when they heat it up, it has the same thermal conductivity, and then we get three different axes. Wow. I think I forgot to take one of my allergy pills today. Excuse me. Okay, so they start with everything kind of going off in all directions, but as it forms into its more crystallite, we see a difference in conductivity between the X, Y, and Z axis. Okay. And that has, and the reason you get that increased that's right. The reason we have persistence length versus radius of gyration. So persistence length is how long it looks, and radius of gyration is the end-to-end mean distance, right? So as your dihedral angle gets tighter and tighter and held in place more and more, it means it gets more rigid, okay? As you force it into a one configuration only, it gets more rigid. And that if it gets more rigid, its thermal conductivity is going to go up. Yeah, that's what okay. So I said before that the ultra high density, ultra high molecular polyethylene has a higher thermal conductivity than polyethylene. Okay. And so when you look at the effect of side chains are, things that will disrupt order and disrupt and leave, a one chain bent to get around that side group. And so this study was done where they looked at the different side groups for different lengths. And so it's how many side groups you have per 50 segments, 75 segments, and 100 segments, and how did that affect the thermal conductivity? So if you have a side group every 50 segments, you have the lowest thermal conductivity of your system here. And so in that case, it's the black bars here. If you have one defect, and this is a phenyl group with an oxygen, this is just a phenyl group, this is an ethyl group, this is a methyl group, this is, ethylene oxide group, methylene oxide group, ethyl group, vinyl group, and a hydroxyl. Okay, so they're changing the different groups, but they see the same trend. Okay, if you have one substitution every 50 segments, you have the lowest thermal conductivity of the set. Okay, if you extend that by 25 segments to make it 75 segments between defects, the thermal conductivity goes up. And if you extend it again, another 25 segments, the thermal conductivity goes up again. So that's saying how perfect your polymer is or how few defects your polymer has will dynamically affect your thermal conductivity. And the less defects you have, the more thermal conductivity.
It looks like the size of the side chain also affects it.
Well, I think this is smaller.
Right. So the bigger ones, I would assume, have more of an effect. Starting with nature.
Well, the benzene here is bigger.
Right.
So it has the lower thermal conductivity to begin with. So, and this is the smallest one, or no, this is the smallest one. So yeah, you're right. It is, the smaller the group, the less it affects the baseline thermal conductivity as well, because the thermal conductivities do go up with size. I didn't notice that. Thank you.
So in like the graph 2 slides ago, where we talked about where the oxygen's on there and lowers them. So wouldn't you just put a hydrocarbon chain on there, small hydrocarbon chain like that?
Well, in comparing this to the other one,
Yeah.
okay, so they do try that. There is small hydrocarbon chains on this. So if you look at the bottom here, they do use small hydrocarbon chains right here, and they do seem, well, this one actually does affect it quite a bit, but these two oxygens are right here. So it looks like the size of those chains are right about the same level. But this one definitely is the smallest group here and has the least effect on the thermal conductivity.
And the largest one.
Yeah, and the benzene ring is definitely the largest one. Okay, does that make sense? I think I'm gonna get that tattooed on my arm. Okay, so I said hydrogen bonding can affect things too, okay? So the more you can bond to things, so it doesn't just have to be a covalent bond, it can be any other type of strong bond that can add to the thermal conductivity. In this case here, what they did was they took polymers with varying degrees of hydrogen bonding ability between them, okay? So we have one here, this one right here has no hydrogens to hydrogen bond. This is polyacrylic acid, which has one hydrogen per repeat unit. And so it can make a strong hydrogen bond between this polyamide here and this polyacrylic acid. Okay. Then what they did was they took it and said, okay, this acid will have a strong hydrogen bond, but we can move it to an alcohol and that'll have a hydrogen bond, but it'll be a weaker hydrogen bond because the acid is more acidic and therefore has a stronger hydrogen bond. This one's less acidic and has a less. And then they took it and actually did an intermediate one. The pKa of phenol is about 10. The pKa of an alcohol is about 15. So phenol is actually more acidic. Okay. The pKa of acetic acid is 5. So you have 5, 10, and 15. So that's actually a pretty neat strength difference there. So the 5 is stronger, the 10 is intermediate, and the 15 is the weakest. Okay, but what they see here is that when you have a heterogeneously distributed system, so one of the polymers, or they have short and long chains here. And so when they have them and they don't have strong hydrogen bonding, the thermal, you have to, have, this is the total interconnection here, and then has to jump through the matrix to get to this one. And then this has a thermal conductivity pathway, but then it has to jump through the matrix to get this one. Okay. Now, if instead of having that matrix interaction where you have to go through the weaker bonds, what if you had hydrogen bonding between all the different segments? What if you had these hydrogen bonds now forming in between these long segments right here? So what that now does is that makes that you now have a hydrogen bonds is part of your thermal pathway, giving you a shorter thermal pathway, therefore a higher thermal conductivity. Okay, so what they see also is that there's an effect where it goes up to a certain point, up to a certain mole fraction of your hydrogen bonder here. Okay, and then it goes down. Okay, so when you add more polyacrylic acid, then you have things to hydrogen bond to it. It starts to be just the thermal conductivity of the polyacrylic acid, just thermally hydrogen bonding to itself. Okay. Now, in the case of the weak one, there was, you saw some improvement, not as much, because notice this would be right here on this graph. So there's not as much of a change. But it goes down to, this is the pure polymer, this is the pure polymer. Adding the hydrogen bonder helps initially. After the 50% point, it drops back down. It's only hydrogen bonding with itself. And so it brings back to that other pure polymer thermal conductivity. And in the intermediate, we actually don't see any enhancement at all. So it's just that it's not creating those thermal pathways in this system. But notice the enhancement here. It's almost 2.5. So it jumps 250%. Okay. But it's only at that 30% mole fraction. I believe it's volume fraction. So that's one of the effects of hydrogen bonding. And the next thing you also get with hydrogen bonding is, if you have things that want to bond to themselves more than other things, right? They're going to form little clusters, right? And there's a couple different ways that you can look at this. And in this particular one, they're looking at the hydrogen bonding between PVA, which is polyvinyl alcohol, gelatin, which is a protein, and lignin, which is a nitrogen-containing protein. And they have the little structures here. And so what you'll see here is that they can all hydrogen bond to each other. The PVA can only hydrogen bond to the lignin and the gelatin because that has the most acidic protons, I think. Yeah. And so we'll see that that is how they're kind of ordering. So when they first order, they can order into small clusters, medium clusters, or large clusters. Now those little clusters, they have the hydrogen bonding in between them, but there's no hydrogen inside the cluster. There's hydrogen bonding. So there's higher thermal conductivity inside the cluster, but then you have the interface. Okay, so now if we look at that interface here, if you have just clusters kind of stacked around each other, you're going to have to go from this cluster interface, this cluster interface, this cluster interface. Okay, so each of those interfaces decreases your thermal conductivity. Now, if you have bigger clusters, then you might be able to get a lot more through before you have an interface and get to this. But what if you, instead of aggregating into clusters, what if your clusters merge together to give you kind of a coiled like a protein or something that was coiled and has a hyper superstructure right here? What you're going to do is you're going to enable it to just transfer all the way along that coil. And you're going to get a higher thermal conductivity. And this can be controlled. This hydrogen bonding can be controlled by thermally cycling your system, making it break hydrogen bonds and form new hydrogen bonds and get a longer persistence length. And that longer persistence length is going to give you higher. Okay.
So this is just polymers, right?
This is just polymer clusters, yes. So yeah, they're using the different size clusters to measure different thermal conductivities. So they actually can aggregate, they start with small clusters and then they can thermally cycle it to get those larger and larger clusters. And they see an enhancement of the thermal conductivity. So another way to do it, how else can you get strong bonds, is you add more covalent bonds, and adding covalent bonds by doing, in this case, cross-linking here. And so if we look at just looking at through our conventional bonds, just the covalent bonds, the energy transferred from that, that's the normalized thermal conductance there. So some of the approach is that just the covalent bond, but when they take into account all other interactions, hydrogen bonding, pi stacking, order, crystallinity, all these other things, they actually contribute a little bit more to the total normalized thermal conductivity. So not just the bonds that make it happen, but it helps. If you didn't have cross-linking before and you do now, it will enhance your thermal conductivity. Okay, so that's just how you can increase it in just the polymers, no composite at all. Okay, so let's look at how we can do it with our nanocomposites. So when we talk about without an interfiller network, okay, so your filler is your nanomaterial, and without an interfiller network, meaning you don't have a full network going through your system. So how can you change that? And so that happens a lot when you have these aggregation domains. We saw that before, where it went up and then it went down, right? They're showing the same thing here. As we start adding multi-walled carbon nanotubes to polypropylene, we see an initial uptick from polypropylene, getting a really good enhancement, almost double here at this about 2.5 weight%, and then it drops off, but then it goes up again. Okay, it drops off because we've hit an aggregation threshold. They start to aggregate, but then why does it pick up again? We have enough volume fraction of the aggregates to increase our conductivity. So this drop off here is due to aggregation, but now we have enough aggregates that we can actually jump from aggregate to aggregate to aggregate to still do the thermal conductivity. In fact, if we went, this would probably go up a little higher if they went up to higher levels. Okay, so do we see how not having you can have a well-dispersed system that will have that interpenetration, that network made, and then you can lose it all by aggregation and greatly affected by processing as well. Okay, so then I introduced the topic of interfacial thermal resistance. Okay, and that's where we have our very conductive material, and then we have the interface between our very conductive material and our matrix, which is a poorly conductive material, thermally conductive. And so there's that resistance to do that. And so if you can do something to change that, if you can chemically bind it, or in the case of like clays, make them molecularly constrained so they have less motion, you can change that thermal interface. And this right here, this study was actually kind of interesting in the fact that they figured out that by doing different loadings and graphing the conductivity versus divided by the conductivity in the matrix itself, okay, as a function, and then measured the thermal interface resistance here, they saw that there was a crossover point, okay, and that crossover point is what they call their critical value, and that is basically they've actually found that's the resistance of the matrix, between the matrix and the nanofiller, okay, and so they were able to identify it at different loadings. So that was one way that they measured it. Now that they know they have it, now how you modify it? Well, you can modify it by changing the interface conductance by modification of the compound. So in this case, I'm going to do 1D thermal conductivity, which is carbon nanotubes. Again, it's 1D thermal conductivity because it goes down the length. Okay. So what we see here is by modifying the surface of the carbon nanotube with different things, octane, a hydroxyl, or this HLK5 is just the bare pristine, that's with no modification. What we see here is the scaled conductivity as you increase the surface coverage ratio. No, this should be the oh no, this is versus scaled versus the unmodified one. I don't know what this modification is, I forgot, sorry. But with an octyl hydroxyl group, it starts out pretty high thermal conductivity, but then as you hydroxylate it more and more, it goes down. So your hydroxyl groups are forcing it out of the matrix. It's not enhancing that thermal conductivity at the interface, and therefore it's decreasing. In this case here, we have octane modified. It, again, as you load it up, as you put too much on there, it becomes the barrier to thermal conductivity. It helps initially because of the inner penetration of the matrix, but it hurts after if you're pushing the matrix out too far away from it in too many spaces. And again, with this other filler, it does with a little bit less of a detriment as you increase the filler up to even like 15% here. You only decrease its relative conductivity a little bit. So what this shows is that, number one, the modification itself is important, and the concentration of the modification is important. You want something that's going to interface with the matrix very strongly and be compatible with that matrix to make that interface, that barrier, as small as possible and as thermally resistive as little as thermally resistive as possible.
So it's like HLK5 polymer that alternates between like the side of the phenol group and then this phenol group.
Oh, okay. Oh, so it's a rigid broad polymer.
Seems like it.
Okay. So what you're saying is,
Yes, and well, and
those are
close enough.
those are ends there.
No, no,
It's not a diazo. It's a
no, it would be just like an ethylene,
oh.
polyethylene phenol group coming off of it, and then
Polyethylene with a phenyl group. Oh, okay.
yeah, that,
With an
and then on that, there's a group in between that, but at the end of it is that.
okay.
And there's like a small hydrocarbon chain between the
Okay. So we have these right here that can pi bond to the surface of the carbon wall nanotube, and the polyethylene that can interface with the polymer. So, okay, that makes sense. They do a lot of stuff where you put in things like octyl benzene, and the benzene will stack with the graphenes, and then they'll have that chain coming off to help solubilize it. Okay. So in this one, they actually were looking at the interface between the polymer right here, and they're modeling it. So this is the particle here, and then the interface is this area right here around it. And what they saw was by adding more and more functionalization, you start pushing the matrix away from the conductive material, increasing the thermal resistance. So there's a fine line between pulling your matrix in tight and pushing your matrix away. And so what they found is that even at these low functionalizations, 10% is probably closer to what you really want for your system, because it doesn't, this is resistance to heat flow, by the way. You can see that. And so, and this is doing it in carbon nanotubes in a polyethylene. So in the case of this, if you add too many carbon atoms to that outside of that carbon nanotube, it's just going to push the matrix away. Okay, so let's talk about enhancing on 2D systems. So we're talking about graphene and boron nitride, right? Because it's got an XY axis of thermal transfer. And what they found was they also see a difference in the amount of grafting, okay? You want to have a little bit to get it compatibilized, but you want to have as much of the pristine thermally conductive surface touching the matrix as possible. And what they found was at a very low rate of about 1%, they saw their best result. And again, this is a ratio of the thermal conductivity divided by the thermal conductivity of the matrix. Okay, so in this one here, by having it with different volume fractions, this is 1 volume fraction, 6 volume fraction, and 10 volume fraction. Okay, so look at this low grafting density, low volume fraction has the greatest change in the thermal conductivity. Okay, it's not aggregating, it's dispersing really well, it's interfaced with the polymer really well. So you found, it's not just if one's good, 100's better. There's really a sweet spot on here. And here it's about 1% at a 1% volume fraction loading. So, and that's a graphene right there. Okay, and so the thermal conductivity perpendicular to the plane is proportional to the grafting density, while the in-plane thermal conductivity sharply drops as the grafting density increases. I had to pull that out of the paper because I wasn't going to remember. Okay, so let's do another way to improve it. So that was thermal resistance. That was that thermal barrier going from your conductive filler to your matrix, okay? So let's talk about another way to improve thermal conductivity in your nanocomposite. And obviously we've seen this before, is improved filler distribution. How, if you get your stuff to not aggregate, you're going to get a much better process. In this case here, they were looking at 2 different things. They were looking at multi-walled carbon nanotubes in polyimide, okay? But then they were using cubic boron nitride, okay, in there. And so this is more of, those are rods right here. And so they're both one-dimensional thermal conductors here. And what they see is they get an immediate jump from the pure polymer here with a loading of some, but then after a while, these start aggregating. The carbon nanotubes start aggregating. But the boron nitride breaks up that aggregation. Adding a little bit of boron nitride acts as like little spacers, little thermally conductive spacers between those bundles and doesn't let them aggregate. And we actually see that enhanced thermal conductivity. So disrupting its attempt to aggregate turns out to be a good thing in this case here. So that adds to a higher degree of the thermal conductivity. So let's talk about interfiller networks now. Okay, so what we're saying here is we're going to do some kind of processing to make sure that we have an interconnect as much as possible with all the filler we have. Okay, so that usually takes some kind of processing or some kind of thing that helps you disperse your material really, really well. Okay, so in this case here, what we're going to do is we're going to take raw carbon fiber, just as made. We're going to copper coat that carbon fiber. And then we're going to use a bonding agent. In this case, it's a mercaptosilane, meaning that the sulfur part is going to stick to the copper, leaving the silane to stick to the matrix. Okay. And then we're going to use the matrix of silicone rubber. Okay. So what we see here is silicone rubber, thermal conductivity is here by itself. Okay. And then by just adding some raw carbon nanotubes here, let me change colors here. By adding the raw carbon, we get just this kind of mole fraction effect here. So just the fibers interacting with themselves, whatever that thermal junction is, that's what we see. Now, by making them slightly more thermally conductive, adding copper to the outside of them actually makes them more thermally conductive because copper has a higher thermal conductivity. It actually jumps right here. And then adding our coupling agent to the copper to make it try to bind stronger into the matrix actually didn't work. You see, it actually doesn't have as high a thermal conductivity. It didn't help. It's actually acting as a spacer. The copper is completely covered with this binding agent, and that spaces it away from the matrix, giving us a higher a little bit higher barrier to get into there. I mean, it's not a lot of an effect, but it's definitely an effect. So if we were going to do this, would we want to actually add that coupling agent to this thing? Probably not. The copper itself would be fine. And we definitely would want to use the raw carbon fiber. Okay. So let's go to 1D fillers now. So in 1D fillers, you have to disperse them out, and they have to be the long persistence length. And it has everything to do with the randomness of the dispersion of your tubes. You actually would prefer to have them contact once or twice, or maybe even 3 times along their length, to help create the number of thermal pathways through the system. And so in this case here, what they found was that by looking at different volume fractions of their material, these are well dispersed into their system. They looked at cellulose nanofibers, which are thermally conductive more than the matrix, carbon nanotubes, and metallic nanowires. And what we see is there's different slopes for their volume fractions here. We see a nice line for our cellulose nanofibers, but it's not as high as an effect as some of the other ones. Here, below here, this is almost 0, so you'll see almost no effect. But once you load it up to a certain point, you get your carbon nanotubes actually have the highest conductivity at that mole fraction, and the metallic nanowires have that. So what do we see here? What's the reason for this? So maybe the persistence length on the carbon nanotubes is higher, and so we have more carbon nanotubes touching more carbon nanotubes, giving us more and more pathways for that thermal conductivity.
So just like
Yeah.
theoretically, if you kept increasing it, it would keep going higher, right? There's not really, you would just lose the mechanical benefits of having it.
Let's see, this is only up to 0.1 volume percent, so you could go up a lot higher and still get both thermal and mechanical properties before it got too brittle.
Is that percent?
This is mole fraction, volume fraction, sorry.
So it is 0.1% volume fraction.
Yeah. And the thermal conductivity here range is actually significant here. It's going from 0.1 to 100. That's 3 orders of magnitude. So we had those one-dimensional and those two-dimensional fillers. Well, obviously they each have, a processing problem, and they each have an advantage and a disadvantage. Why not take them and combine all of them using a 0D filler, which would be spherical, because it doesn't have a long persistence length. The 1D, which would be the nanotubes, and the 2D, which would be the plates. And so there's a bunch of different ways to do these by mixing different fillers in. And so we're going to look at each of these as a function of how they enhance the thermal conductivity. So in the case of the 0D, 1D, you basically are wanting your 0Ds to be big enough to have 1 or 2 contacts with your 1D material. And so hopefully your 1D material is bridging your 0D materials. And so it can jump from space to space to space. In the 2D materials, you actually can have that one platelet touching 2 or 3 different 0D spacing. And so that's going to give you a different kind of enhancement. You're going to see a different kind of enhancement curve. And then, of course, the last one would be the one we've already looked at with graphene and multi-walled carbon nanotubes. In the graphene multi-walled nanotubes, we saw that the 1D and the plates had an enhanced effect to a certain point, and then aggregation took over. Okay, so let's look at the 0D, 1D hybrid. And in this case here, we're going to use polyvinylidene difluoride and polystyrene blends. And the fillers that we're going to be using are, let's see, silicon carbide. So it's silicon carbide spheres. Okay, silicon carbide, again, very tight bond, very thermally conductive material. And then they're going to use multi-walled carbon nanotubes to disperse it in there. And so what they started with is with just the matrix itself, we have a very low thermal conductivity here. If we just use the carbon nanotubes at a 5 volume percent filler, we get a slight enhancement. This is just with the silicon carbide. So silicon carbide actually has a really good curve here. For a zero-dimensional material, that's a pretty good curve. And they account that because they actually kind of aggregated some of them together as well. They didn't, the picture is actually the one with the hybrid, with both of them in there. And in this case, the hybrid one is where the carbon nanotubes are bridging the gaps in between all the different silicon carbides, okay, giving us a greater enhancement and a higher slope. So I find it very interesting that they didn't do higher loadings of the carbon nanotubes, but maybe everybody's already done that. But the fact that their silicon carbide nanoparticle gives such a good response without them, but isn't a better response with them. So that's what the first hybrid system is, the 0D1D filler. 0D2D filler would be more like the spheres and graphene. So in this case here, we're looking at different filler contents, and they're using boron nitride, and they're using aluminum oxide. And in this one, the aluminum oxide is the 2D material. It's aluminum oxide. No, the boron nitride is the 2D material, sorry. Hexagonal boron nitride is the 2D material. And then silicon oxide, aluminum oxide is the 0D material. Okay, so if we have just the boron nitride platelets, the hexagonal boron nitride platelets, when they form a matrix here, we can get a nice thermal conductivity going through here in this range, okay, at a decent loading factor. Notice this loading factor is 10% right here. And so we get a decent effect here. And so this is the one with the boron nitride by itself, is in black on the bottom, right here. And it has the platelets. The platelets have to kind of arrange. You'd think that they'd have a better thermal conductivity, but it doesn't. Then this blue line here is just the aluminum oxide. Again, that's a really good response for a 0D material. But adding them both together means that they can transfer heat in between the particles as it goes through, giving us that enhanced effect on this last line here. So, but it goes down with the amount of aluminum you use, okay? If you use up to maybe 10 weight% alumina, and then beyond that, it goes down. Why? Boron nitride actually has 2 orders of magnitude higher thermal conductivity than the aluminum oxide does. Okay. But so when we see that this is where we have boron nitride contacting alumina, contacting boron nitride, contacting aluminum, contacting boron nitride. By the time we reach here, now we're starting to say alumina, alumina, alumina. And so we're getting just the alumina interactions. And therefore, we're starting to go back down to alumina by itself. So we see an effect where you want to interconnect those alumina particles, but once you get too many of them, you can't interconnect them with the boron nitride, and the synergy drops. It goes away. All right. So let's go on to, okay, I'm not going to finish all these slides. Oh well. We'll just have the testing. Okay, so let's see. On this one, we have a graphene and multi-walled carbon nanotubes. So it's a 2D, 1D. And so we've seen this before, where we have just the graphene by itself does okay. Just the nanoballs by themselves do okay. But when you add them together, you get this, interconnection. Half the time it's on a nanotube, half the time it's on a nanoplate. And you see that, in this system here, the graphene oxide is actually, because of its defects, not as good as graphene. Carbon nanotubes are a little bit better, but the synergistic effect between the two, having, number one, you have the platelets to help break up any aggregation you might be forming. You have with the nanotubes, and you have the nanotubes to break up the aggregation for the plates. So they're actually kind of interfering with each other's aggregation, and that allows them to also work well. Okay. So now, this is another way of looking at it, and this is what they called the double networks. In double networks, what they're trying to do is they're trying to improve that network by starting with plates, adding a little bit of carbon nanotubes, and then that gives it a certain network, one network. And then by adding more carbon nanotubes, you have not only the platelet nanotube network, but you have a nanotube network. And so they call it the double network here. And so when we look at this, and this is in high density polyethylene, right here, just the expanded graphene by itself is this curve here, this black curve right here. And then by doing just the carbon nanotubes, there's this slope down here. And then by adding varying amounts of the graphene, expanded graphene to the carbon nanotubes, we see an enhancement because we have this line here is nanotubes with the graphene. Remember, this was just the expanded graphene by itself. This is nanotubes enhancing it, and this is nanotubes enhancing it again. Okay, so those are, it's weird that they start where they do, but the enhancement is definitely marked from their threshold filler, and this is a total filler content of 20%. So you're ratioing the two fillers in your polymer as you go. Okay, and they attributed this to that when you have the single network, you have this zone here. When you have the second network here, you're in this zone here. And when you have the third double percolation, that's when you're in this zone here. You're getting into the different zones of thermal conductivity. And you can also see that in this paper here. We're looking at a different version. Oh, maybe this is the same paper, sorry. Okay, let me double check. 278. Yeah, I think this is the same paper. And what they did was they were measuring thermal conductivity versus fillers here. No, this is an epoxy, sorry, it's different paper. Carbon nanotubes, graphene nanoplates, and then added together, seeing that same synergistic add. And notice that the volume fraction here is getting really high, 50% volume fraction in epoxy. It's probably some pretty brittle epoxy. But if we look at the ratio of the improvement here of versus it's the nanotubes ratio versus just the graphite by itself, graphite nanoplates by itself. So we're basically baselining for the graphite nanoplates by itself. The improvement actually goes up to about in the 40% range, but there's less improvement at this 50% mark. See how this blue line is starting to inflect down a little bit? Well, the red line is still going up. So what they're showing here is basically the difference in these two lines as we go up. And so we see the marked improvement up to that 40%. But after that, technically the conductivity is higher. The enhancement is less. The enhancement is less. Okay, and the last thing I want to talk about is 3D foam fillers. Okay, so these are usually metal foams. This particular one are graphene and carbon foam. So it's amorphous carbon foam and a graphene foam. And so what they do with that is they kind of form this foamy matrix. They take it and center it out at different temperatures. And so you see they have centered out at 1,000 and 2,800 degrees. And 1,000, they have very low thermal conductivities because they are still very disordered and have a lot of defects, a lot of still other materials in there. By the time they bake it out to the higher numbers, we're looking at all of these up here. Okay. So in this case, the carbon foams that they were making had a higher thermal conductivity than the graphite foams they were making. Okay, so I'm not sure if it's because the amorphous carbon would be able to go into all the different struts and sprues they have, and there was less interpenetration through the struts and sprues with the graphene. Don't know why it's less, but they did see a difference. Now, notice also this is density right here. So this is very low density foams. So this is as made. And then as we heat it, they get higher and higher densities. Okay. But then we have this anomalous set right here. Right here. We have a very low density with the graphene, but very high thermal conductivity for the density compared with the other, compared with just the those, yeah, compared with where the unsintered carbon is. But all the graphene ones are right here, low density foams, high thermal conductivity. Okay, so that brings me to my summary. Okay, so from this paper, we got that the improved crystallinity or chain alignment of the polymer enhances the thermal conductivity. Okay, we also saw that the thermal conductivity could be enhanced by interchain coupling through hydrogen bonds or crosslinks. When nanofillers are used, we want to have the thermal conductivity exhibit. In composite, the thermal conductivity could exhibit non-monotonic increase trends with filler concentration. It's going to go up and then come down because of aggregation. So stopping aggregation from those fillers, or looking at the filler matrix interfacial thermal resistance. We talked about that quite a bit today. And then to prevent aggregation of nanofillers and nano fibers, you often need to have them functionalized. We saw most of the time when you functionalize something, it worked. Sometimes it didn't, but most of the time it did. Nanocomposites filled uniformly distributed fillers. Thermal conductivity increases slowly until there's a percolation threshold. And that percolation threshold is having a clear path for the phonon to travel. So it's not that electrical one, but it's the similar one. It's usually much higher loading than for electrical. Then it grows rapidly in convergence on a constant value, because that's going to be the most thermally conductive it can be is the filler by itself. Okay, and then the 3D fillers could be more effective than hybrid fillers to enhance conductivity because of the 3D network, and that means the foams. There's already a three-dimensional foam in there. And then what you would do with those foams is you would actually take them and infuse them with whatever polymer you want. So if you wanted it rubbery, you do it polyurethane, or if you wanted it rigid, you do it epoxy. And then that would give you, that entire thing would have uniform thermal conductivity in all three directions. Okay, so the last thing I want to do is kind of remind you that we have different kinds of these fillers. And some of these fillers are electrically conductive. Okay, so some applications you do not want to use these. So, well, all of these are good. Clays are good because they're they're one-dimensional but have two planes of thermal conductivity. These are nice and cheap. These are a little harder to work with. This is really good but expensive. That's really good but expensive. But if you want thermal conductivity but not electrical conductivity, you're down to these four. I want to make sure that you looked at those. All those carbon ones are all conductive, electrically conductive. Okay. Now they're also low density, so that's a good thing too. So when we're looking for these, we're looking at clays, and for our lower density side, and titanium oxide for our higher density side. So
This might be a really simplistic question, but the reason that the graphene and the CNTs are conductive, but the nanodiamond isn't, is because of the double bonds, right?
yes, conjugation. That is the exact right. Yes. So that is my last slide. And so, hey, I finished. Okay, any questions there, Jacob? I know you're asleep.
No, I'm good. Thank you.
All right. All right. Well, you take care. See you on Monday, hopefully.
All right. Sounds good. Thank you.
All right. I'm going to stop recording.